University of Sanna. Okay, let's try it again. Mariani. What did I say? Oh, I know what I'm thinking about. So, Mariani from the University of Alzari in Italy, and he'll be speaking about polymer nanocomposites containing real graphene.
Okay. Maybe. No, there is another. Yes, but. Okay. Thank you very much. Good morning. So, first of all, I'd like to thank the organizer for inviting me here, and in a special way, my good friend, Professor Nessoli. Thank you very much. The title of this presentation is a little bit strange because I use the word real graphene, and the reason will be evident in a moment. So, as you well know, graphene is any single layer which constitutes graphite, and approximately in 1 millimeter of graphite you can have 2.5 million of graphene layers. And graphene is characterized by structural perfection. It is constituted only by carbon atoms. All of them are sp2 hybridized, and it's considered a bidimensional crystal. We use graphene for thousands of years, actually, when we write. But something strange happens in 2004 when two people decided to do a strange experiment. They put a graphite flake between two faces of a Scotch tape, and I did this job for a number of times, and after sometimes they were able to isolate single layers of graphene. Thank you, it's working. At that time they decided to write a manuscript and to send that manuscript with this finding to Nature, but Nature rejected it. So they decided to send again the same manuscript to Nature, and Nature rejected it again. After that, they decided to send that manuscript to Science, and Science decided to publish it, and it was 2004. From 2004 and 2008, an increasing, a very huge number of papers devoted to graphene were published. Devoted to the obtainment of graphene and to the use of graphene. In 2010, these two people, Roberta and Javier, were awarded a Nobel Prize in Physics. So, as I told you, it's characterized by structural perfections, and you have a conjugation along all the, let's say, macromolecule, or all the layer, with all the atoms which are sp2 hybridized. This is a real graphene. Due to these characteristics, graphene is characterized by some outstanding properties. For example, it's characterized by high electron conductivity, high thermal conductivity, high Young modules, more or less that of dynamo, high surface area, transparency, and so on. All these features are so good that a lot of scientists are studying it in order to find new applications. And the applications are in a lot of fields, for example, in biology, gastric detection, solar cell, electronics, and so on. But they are particularly interested in the nanocomposite, and in particular, polymer composite, which is the field that I am interested in. These are the methods proposed for obtaining graphene of the so-called graphene. Indeed, this is the method proposed by Roberta and Javier, micromechanical cleavage. It means Scotch tape. And other methods were proposed. One of the most used, for example, is chemical vapor deposition of the epitaxial growth. But almost all of them give rise to something that is not real graphene. I will tell you something more about this method. This is liquid phase exfoliation. Liquid phase exfoliation is divided in two, actually. In general, most of people do the following. They start from graphite, they oxidize graphite. What they get is graphite oxide, which is characterized by the presence of oxygen-containing groups. It means also that carbon atoms are not sp2, but now there are a lot of sp3 hybridized carbon atoms. It means that the conjugation is destroyed. It means that it's a completely different compound. For example, it's characterized by a completely different polarity and a completely different solubility. However, graphite oxide is so polar that can be dissolved in some polar media by sonication, for example. So from graphite oxide, you can have graphene oxide after exfoliation. And if you reduce graphene oxide, you obtain something else. What? Some people, most people, call it graphene. But it's not. Why not? Because there are a huge number of oxygen-containing groups, and so we can call it reduced graphene oxide, but not graphene. There is another method, a method developed independently by my group and a group of Polymer in Dublin. It's similar because we start from graphite, but we don't oxidize it. We just sonicate it in a proper liquid medium, and we obtain directly graphene. It means that in this case, what you obtain is real graphene because there is no chemical manipulation. It's the same graphene made by Novoselov and Jane. These are the only two methods that allow obtaining real graphene, so, at present, obviously. The method is very simple, and we tried it in several liquid media. The best we found is this one. It's a monomer. We are interested in polymer nanocomposites, so we try to use monomer if possible. And we just sonicate for 24 hours, then we centrifugate, and what you obtain is a graphene dispersion. Now, so if this method is so easy, fast, and give rise to real graphene, why people do not use it? And this is a question I don't have a real answer. But I wonder, if you, or at least when I start a new research, the first thing I do is reading some reviews on this new topic for me. And there are two main reviews on polymer nanocomposites containing graphene. And one is by Ruoff, and the second is by Makosko. There are hundreds of references cited in these reviews, but only two are about the liquid exfoliation of graphite directly to graphene. What are the other methods about? The other methods are about the obtaining of graphene oxide, and this is a very confusing point, because if you read literature, in many papers, you read in the title something graphene, but not graphene oxide. and you have to read very carefully that paper, and if you are lucky, you understand maybe in the experimental, they are not using graphene, but they are using graphene oxide. Maybe these papers are written by physicists, probably. I don't know. Other are about methods to obtain some more or less oxidized forms of graphene. It means chemical or thermal reduced graphene oxide, or graphene nanoplatelets, which are now commercial, but they are again reduced graphene oxide. So most of these papers are not about graphene. I'm not saying that using graphene is better than using graphene oxide or than using reduced graphene oxide. I'm saying that it's different. And the properties are different too. Let's come back to the reviews. This is a table taken from one of them. No? And if you see here, this is a direct sonication of graphite, our method. Disadvantage is low yield. So it's obvious that if I would start my research on this topic, I do not use this method. Why using low yield method? It's obvious. But is it true that this method is characterized by low yield? At the beginning, the first paper published by Polymer was about a concentration of about 0.1 milligram per milliliter of graphene. Low yield. Yes. The first paper. At present, typical concentration of reduced graphene oxide or its more or less derivatives, the more or less oxide derivatives, are in this range, 1 to 5 milligram per milliliter. But if you use the easier method, without any chemical manipulation, you are in this range, 1 to 20 milligram per milliliter, which are the highest concentration of graphene in liquid. So, low yield is not true. But probably that's a reason why people do not use it. I don't know. Because the real question is the following. Why wasting time and money to get something that contains the fact reduced graphene oxide and is obtained on a lower amount? So this is my question. I don't have an answer. Okay, some about our works. We started 4 years ago, more or less, by using an ionic liquid as a dispersing medium. The idea was simply to take directly what was done with the carbon nanotubes. It is reported that sonication in ionic liquids can be useful for carbon nanotube unbundling. And we did the same with graphite. Then we did it by using N-methylpyrrolidone. N-methylpyrrolidone is the solvent used by Coleman, 0.1, remember at the beginning. We found two, by the published on Nature. We not. And then we started with monomers. Why? Because since we are interested in polymer nanocomposite, we say, why not using directly a monomer? In this way, we disperse graphene directly in the monomer, we polymerize directly till the dispersion. We don't have to recover graphene in the solid state, so we prevent any possible reaggregation. risk-taking of graphene. Just some of the liquid, some of them are monomers we use. As you can see that this is the best we found, and this is the ionic liquid I was mentioning, and methylpyrrolidone and other. There are many others that I have not listed here. Okay, I go a little bit faster. I just tell you about two examples. I choose these two examples for two different reasons. The first example is sorry, I'm wasting time. The first example is by using N-methylpyrrolidone. In this case, the monomer is solid, so it was not possible to use the monomer as a dispersing medium. So we use the solvent and then remove the solvent. And the second example is with the monomer, our best monomer, we can say, tetraethylene glycol diacrylate or TEGDA. In the first case, we prepared hydrogens, polynanocomposite in the form of hydrogens. Poly and isoropylamide is a well-known thermoresponsive polymer, and it is characterized by a lower critical solution temperature. Actually, this temperature is at 30 or 32 degrees, and below this temperature, your hydrogen is swollen, but above this temperature, the hydrogen is swollen. The idea is what happens if I add graphene, in particular, what about the generally poor mechanical properties of a hydrogen. We prepare a master batch dispersion in N-methylpyrrolidone, and then we added the monomer. So we have a solution containing monomer, graphene, and methylpyrrolidone, and we diluted it, so we obtained these different dispersions. So then we polymerized it, and we polymerized it first by using the classical polymerization. This means 80 degrees for 1 hour, but what we obtained is here reported. You can see that there are, all of them are aggregates. It means that during the polymerization process, you have the reaggregation of graphene to graphite. Why? Because the polymerization took too long time. So we decided to use a different method, which is widely used in my laboratory, which is the frontal polymerization. I will not explain it now. If you're interested, I can talk about it during the discussion. But by frontal polymerization, you have a very fast conversion in seconds, and you reach high temperature, but this temperature is kept for seconds. It means that the system does not have time to reaggregate. The system is frozen. Indeed, here you can see this is a very homogeneous hydrogen without any graphite flake. The little spots are bubbles, are not graphite aggregates. So this is just to mention the importance that a polymerization technique can have during the preparation of polymer nanocomposites. Okay, go a little bit faster. What about the swelling behavior? We are talking about hydrogens with a lower critical solution temperature, and so we are interested in these aspects. This is the neat polymer hydrogen without graphene. You can see the LCST at about 30 degrees, and the LCT is not affected by the presence of graphene, but the amount of swelling is strongly increased, even for low amount of graphene. It is a common behavior which we are finding. This is probably due to the fact that a layer of graphene can obstacle the possibility of cross-linking between macromolecules that are placed on the different faces of the same layer. So the cross-linking is lesser and the swelling is larger. What about the mechanical properties? The black squares are again those of the neat polymer. You can see that if I increase the amount of graphene, I have an increasing of the module, but this is true only up to a threshold value. After that threshold value, I have a decrease of the module, so the reinforcing effect now is a lubricating effect. And this is also another characteristics of many polymer nanocomposites containing at least real graphene. And this is probably due to the possibility of the layers of some like a sliding doors, we can say, one over the other. The second system, just a couple of words about the second system. The second system is tetraethylene glycol diacrylate, a monomer, in which we directly dispersed graphene and then we polymerized it directly. The highest concentration is here reported. In this case, we used the classical polymerization. It was necessary to use frontal polymerization because we obtained graphene didn't reaggregate during the polymerization process. Scanning electron microscopy, I hope it's visible. This is the neat polymer, and this is the nanocomposite. You can see the big difference between the two images. And what about the properties? For example, glass transition temperature. The neat polymer is characterized by a glass transition temperature at about 1 degrees. But if you increase, if you add a graphene, if you increase this amount, you have an increasing of the glass transition temperature up to 27 degrees. But after that, you find again a threshold value. After that, you have a decrease of Tg, as in the previous case. And this is also confirmed by this other experiment about the mechanical properties, about the module. Again, we have an increase of the module up to the threshold value, and after that, a decreasing of it. Okay. I don't know if it was too long, but I have finished. I have just to summarize what I said. And so the method used for producing graphene can be really very simple. And so it's not necessary to use a strange path, but you can just start from graphite and you can sonicate it. The method doesn't work in all cases, but it's obvious. But you have a good or the most good liquid medium you can obtain directly graphene, and that graphene is without any imperfection, so it is characterized by some properties that can be used. The method is so easy, cheap, fast, and so on. It's also important that you can use a monomer directly where dispersing your graphene, and so you can polymerize it directly without any recovery of this nanofiller, so you obtain directly the nanocomposite. In some cases, during the polymerization process, you can have reaggregation, and so the suggestion is to use a fast polymerization technique. Frontal polymerization is one of them, and it's easy and cheap too. What we observed in these two cases, but it's something quite general in all other systems we have studied, is a large increase in the hydrogen swelling capability, a reinforcing effect up to a threshold value, but a replicating effect after that threshold value. That's all. Thank you very much.
We have time for a few questions.
Have you tried to use any oligoethylene glycol monoacrylate or methacrylate as a dispersing agent?
Yes, we use. I think that your system, the system you are mentioning, are probably the best. The presence of some oxygen in relatively long, low molecular weight molecules seems to be the best. So oligo systems seems to work well.
Monosaturated system, monounsaturated systems, right?
Yeah.
Because I can see the problem you might have when you use the bisacrylate or bismethacrylate is that you're really forming a network, and if you have any fluctuations in the cross-linking density, that would be enough to give you TG changes or swelling behavior changes and so on, and modulus changes.
Yes, but we observe the same behavior in mono. For example, endemic caprolactam without any cross-linking in other systems which are not cross-linked. The behavior is practically the same.
I think it will just be a nice double check.
Okay.
Just to be sure.
Thank you.
Yeah, I have two questions. What are the sonication conditions you used in terms of frequency and power? The second question is, do your nanocomposite have better electric conductivity, thermal conductivity as compared than composites with not real graphene oxide?
So about the first question, we are poor because we are Italian, so we use a very common ultrasound bath for washing. Other people use very huge and very powerful systems, but they work. They do not work as well as our, probably because too high power destroys everything. So you can use your ultrasound mount for glassware. Now the second question was about the properties, for example, electrical properties and so on. This is something that we are studying in collaboration with other groups. One of the groups is that of Professor Kenny, who was here yesterday, but now I don't know. And they are interested in those properties, and I don't have results now.
That's really what you want to show.
Yeah. Yes. In fact.
And the last question,
So the diacrylate that you use as a cross-linking agent is also the best compound to exfoliate graphene.
At present.
So now, if you use it in the presence of another monomer, could the diacrylate partition around graphene so that it's not the concentration or the density of cross-linking points is higher close to graphene, and the more graphene you have, the less cross-linking agent you have in the polymer section, which will give you a decrease in the modulus, or it will break one.
Yes, I think that's. I think it's something similar to what happened as well in behavior, because you have a decrease in the cross-linking degree, and so probably you will also decrease in the properties, if I understood exactly what you were saying.
But at the cross-linking agent